This is AP Calculus AB, and in this video, I'm going to talk about section 8.1, integral as net change. So we're making a little bit of a shift here in our focus in this last unit. What we're going to focus on is going to be applications of integrals. And so really, as we go through this unit, you're going to see some different applications. They're all fairly basic, but what I want you to realize is that we're looking at basic ideas that can be applied in really, really complicated situations. So for today, we're really starting to talk about rate functions. And the main idea is that if we integrate a rate function, we get the net change in whatever that rate is measuring. So as an example of that, we're going to start with motion problems, which we're familiar with. We've worked with these throughout the first and the second semester. But now we're going to use that as a transition into different types of rate functions. So let's start with some motion problems, and then we'll work our way into some different types of rate problems. So on this first problem, it says a particle is moving along a horizontal axis with its velocity given by this function, t squared minus 8 over t plus 1 squared centimeters per second. And we can graph that, but it essentially asks us to find the velocity at 3 different points in time, and then it says, what do these velocities mean? Well, let's just take a look at this. If we evaluated the velocity at 0, and one thing I want to point out, as we work through these questions, a lot of this is going to be done with a calculator today. And a lot of times with these questions, even if they're not calculator questions, I'm not going to go through the integral steps because that's not really what our main focus is. I'm going to assume that you know how to solve using the integration techniques we've discussed, or I'm going to assume that you know how to plug these into the calculator at this point. So what I'm primarily going to do is just talk about conceptually what we're doing to solve these problems. And then as far as the details go of what goes on in the background between the question and the solution, those will be some of the things that maybe we'll discuss in a little more detail in class if you have questions about them. Okay, so let's start with these velocities. So the velocity at time 0, you can see from this function, we would get -8, and they gave us units here of centimeters per second. So what that means is, since we're moving along a horizontal axis, we're moving in the negative direction, or if you want to think of a horizontal axis, we'd be moving left at a rate of 8 centimeters per second. Okay, at time is about 1.25, we get a negative value again, and this time we get about 0.0177. And again, that's centimeters per second. So that tells me I'm still moving to the left, but I'm almost stopped because I have a very, very small rate of change here of 0.0177. So I'm moving to the left at a very slow rate. And then at time is equal to 4, you would get 15.68 centimeters per second. And so in that case, I have a positive velocity. That means I'm moving in the positive direction at a rate of 15.68 centimeters per second. Okay, so let's move on here and start to get into some of the things that are going to involve integration. Okay, so we're going to talk a lot about displacement versus total distance today. So when we talk about displacement, and we've talked about this before as we've gone through the last few units, it's essentially our rate of change times our time. However, a lot of times we have varying rates of change. So we have, a velocity function that is not constant. So when we do our rate times time, we do that essentially with rectangular approximations. And that's what we're looking at here. You see, we've got our velocity multiplied times some delta t. And essentially what we're doing is we're treating velocity as a constant over a very, very tiny interval. And we're getting sort of a sliver of area, if you want to think of your integral in terms of area. And then the integral is going to add up all of those tiny slices of area to create the overall area under the curve, which represents our displacement. So that's what this summation is doing. If we take the limit of that as the size, the delta t approaches 0, that's going to give us the integral value. So in the end, we have these relationships between velocity and position. So the rate of change of position is velocity. And if we integrate the velocity, we get our change in position, or we just get our position, depending on if we're doing a definite integral or an indefinite integral. Okay, so you can see here we've got this velocity function, t squared minus 8 over 1 plus t squared. And that is obviously a velocity function or the rate of change of the position. So let's say we knew the initial position was 9, then we can get the position at time 1. And we could do that in a couple of different ways. One way we could do it is we could go through and say, okay, well, I'm going to just do this on the calculator. And the way to do it on the calculator would be, let's just start with our initial position of 9, and then here's my net change. What I have in this integral is the net change in my position on the time interval from 0 to 1. So we could solve that out by hand. It could be done. But the main idea is we do our position plus the change, and that gives us our end result. Another way you could look at this is the position at time 1 would be the same as the integral from 0 to 1 of the velocity function. And then we would add the 9 to that. So that's essentially what we did, except we actually have the velocity function plugged in. So that's one of the main things I want you to get out of this is, you always want to take your initial position into account, but when you integrate that rate function, it's going to give you the net change. In this case, how far has my position changed from time 0 to time 1? All right, so let's take a look at this same problem in a slightly different way. So now, let's say we want to just say, what's the position at any point in time? Well, this is the exact same setup I had a minute ago, except for now, notice it's going from 0 to t for the limits of integration. And whatever I plug in for the t, that's going to give me the displacement from time 0 to that point in time. And then we're adding the 9 here, which is obviously our initial position. So the question then says, find the position at time 5 using your calculator. Well, what you would do on your calculator to find the position at time 5 is we would just do the position at time 5 would be equal to the integral from 0 to 5 of that velocity function. And then we just add 9 to that. And when you do that, you get a position at time 5 of 44 centimeters. Okay, so fairly simple to do and easy to understand what's going on because we're talking about motion and everybody's pretty comfortable working with motion problems at this point. Okay, now another way that we could think about this is as a differential equation. This ties into what we did in the last unit. So we've got this differential equation, ds dt is t squared minus 8 over t plus 1 squared. Well, we could go through and we could separate our variables and we could integrate and we could go through the exact same process and we get the exact same answers. But in this case, I would be getting a position function as opposed to doing it on the calculator and getting the change plus the initial position. Now I would just be getting a position at any point in time. And so I'll show you what the result of this one is if we were to solve it out. Okay, so using the steps that we used in the last unit when we solved differential equations, you can see I separated the variables. I took my antiderivatives. I've got my general solution. Then I use the initial condition of the position at time 0 is 9, and I solve for that c value. And now I've got the position at any point in time. And if I want position at time 0, I just plug in 0 for t, position at time 1, plug in 1 for t, position at time 5, plug in 5 for t. This would give me the exact same set of solutions as what I just found in the previous problems that we were looking at. The difference here is I'm not using the calculator, right? I had to go through and do all this work by hand and get this position function, but the end result is the same. I'm just gathering my information in a different way than I used when I did it with the calculator and integrated that velocity function. Okay, so here's an example that I want you to try. So we've got this velocity function, and there are 4 questions that go along with it. So they notice that we've got a domain here from 0 to pi over 2, and the questions: when's the particle moving in different directions, find the displacement, find the position at a certain point in time, and then it also says find the total distance. Now, the thing that I want you to remember, and just a reminder, when it says total distance, that's just like the total area problems that we were looking at previously. So displacement is going to be net change, so it's just an integral value. But when I talk about total distance, I'm talking about getting how far did I actually move. So the area between my time axis and my function, my velocity function, I want all that area to be treated as a positive. So make sure you think about how you could do that with the calculator as you work through that problem. So I'll give you a couple of minutes. So pause the video. When you come back, I'll show you the solution. Okay, so here's what you come up with for that one. You can see that really everything I did here was on the calculator. So I just graphed my function on the calculator, 6 sine 3t, I set it equal to 0. So essentially just I'm looking on the graph, where does it cross over 0? So I had pi over 3. That's actually where my velocity is 0. So that means I'm stopped. And then the velocity was positive from 0 to pi over 3. That means I'm moving to the right. The velocity was negative from pi over 3 to pi over 2. That means I'm moving to the left. So all we're doing is interpreting the graph, right? We've done all this stuff before. We've talked about, concave up, concave down, increasing, decreasing. We're doing the same kind of thing here, just now in a motion problem. Okay, B, find the displacement on the time interval 0 to pi over 2. I'm just integrating the velocity function. Now, one thing to notice here, I did show what I did, but I don't need to rewrite the name of the function if I'm just going to do this on the calculator. So V of t is already defined. So I'm just showing that on the calculator, I'm integrating from 0 to pi over 2, that velocity function, and I got a displacement of 2. Okay, C, same idea. Find the position at time is 3. Initial position at 0 is 3, and find its position when time is pi over 2. So I'm starting with my initial position of 3, and then this is my net change, and the end result is I'm now at a position of 5. So I've essentially moved 2 units to the right, which is what we saw in the last problem. The displacement from time 0 to time pi over 2 was 2 units. So I've moved 2 units to the right from the initial position, so I'm at a position of 5. And then the last one, find the total distance traveled. Well, now, again, I'm using a calculator, so I'm essentially thinking about total area. So I took the absolute value of my velocity, integrated from 0 to pi over 2, and that's going to give me all of those areas added together, and it gives me a net result of, a total result of 6. Now, notice that when I did my displacement, that's like a net area. So everything above the axis gets treated as positive. Everything below gets treated as negative. We got a net result of 2. But for a total area, we got 6, and that's my total distance. Okay, so let's move on here. Remember that distance is always going to be positive. So whenever they ask you to find distance traveled, it should always be positive. If we were to solve that last problem out by hand, remember we had negative velocities and positive velocities. We would have to break that into 2 parts. And we've done this before as well in terms of areas when we were looking at integrals. So I would have to break that apart into 2 pieces, and then I'd have to solve those integrals out. Since the second integral is going to be negative, that's why there's a subtraction here, because I'll subtract the negative, and that would give me the total distance. Okay, so from a vector perspective, as you get into higher level calculus, when you go into, if you take calculus BC next year, or calculus 2, you'll start to get into vector calculus. And that allows us to transform calculus from 2 dimensions into 3 dimensions and really beyond that if necessary. So a lot of what we do from a motion perspective can be thought of in the same way as what you think of with vectors. So when we talk about distance or we talk about speed, those are scalar values. That means they don't have a direction associated with them. When we talk about displacement and velocity, those are vectors. That means they have a magnitude or a size and a direction. Okay, so remember that distance and speed are just scalar values. That's why we're always thinking about absolute value when we think about distance or speed. When we think about displacement and velocity, those both have negatives and positives associated with them. Okay, so just to make it really clear, when we talk about distance versus displacement, I just wanted to show you kind of a quick intuitive example here. So let's say Austin to Dallas, we're going to do this drive. And Austin to Dallas is roughly 200 miles to make that drive. So let's say we're going to drive from Austin to Dallas, and then we're going to drive back to Waco. Well, Dallas to Waco, again, this is just kind of an estimate, is roughly 100 miles. So I'm using nice round numbers to make these calculations easy. But let's say I drove from Austin to Dallas and then back to Waco. Well, the total distance that I've driven is 300 miles, right? But if you think about the displacement, how far am I from my starting point? Well, I went 200 miles away, and now I came back towards my starting point by 100 miles. So my displacement is actually only 100 miles. I'm 100 miles from where I started. So keep that in mind. You can always think through these things when you have these motion problems. Just try to think about things that relate to things that make sense to you in real life. And it usually becomes pretty easy to reason through these. Okay, so as a general rule, and I'm going to focus a lot on calculator today. As a general rule, if you're finding displacement, you just integrate the velocity function. If you're finding distance, integrate the absolute value of the velocity function. Okay, so let's take a look at some other types of problems here. And we've been focusing on, motion problems, which are things that people kind of wrap their heads around very easily. But now what I want to show you is that those same ideas can be applied to any type of a rate function in terms of the relationships. So this first example, we're just going to do this on the calculator, and we'll talk about the calculator steps a little bit more in class, but I'm just going to go through kind of the setup for these. So the problem says the number of gallons of water in a tank t minutes after the tank has started to drain is Q of t equals 200 times 30 minus t squared. Okay, so that's sort of our scenario here. We are talking about number of gallons of water in a tank. So this is actually not a rate function because that is telling me the number of gallons. So you always want to read these prompts very, very carefully so you know what you're sort of interpreting. A, how fast is the water running out at the end of 10 minutes? Indicate units of measure. So this is a measurement of, Q of t is a measurement of number of gallons. So I'm going to have to take the derivative of that. And again, this would be done on the calculator, but I could just take the derivative of Q, the function Q, at time is equal to 10, and we would actually find that it's negative 8,000. And think about the units here. We had gallons, we took a derivative with respect to time, so we're going to end up with gallons per minute. Okay, so that's telling me then how fast is the water running out? The water is running out at 8,000 gallons per minute, or the amount of water is decreasing at a rate of 8,000 gallons per minute. Okay, part B. What is the average rate at which the water flows out in the time interval 0 to 10? So I want my average rate. Okay, so here's my average rate. So remember, if I want average rate of change, that's just the slope. So I'm going to take the amount that I have at time 10 minus the amount that I have at time 0, and then I'm going to divide by the change in time. And think about the units again, right? I'm looking for a rate. In the numerator, I have gallons. In the denominator, I have minutes. And in the end, this is going to give me a value of negative 10,000. And that would be, again, in gallons per minute. Okay, so fairly simple to do, but the big thing is you've got to start to think about what's happening with your units, what's happening with the scenario that we're dealing with. And the units are usually a pretty good tip-off in terms of, am I talking about an integral? Am I talking about a derivative? What happens when I take the integral? If we look at units, we can analyze all of those things. All right, let's look at another one, and then I'll have you try one of these. So this one says the rate at which water is sprayed on a field of vegetables is given by this function. R of t is 2 times the square root of t plus 5t squared, where t is in minutes and R of t is in gallons per minute. Okay, so notice that we're in gallons per minute. So this is a rate function, and they very clearly said this is a rate function. So write a function Wt that can be used to determine the amount of water sprayed on the field at any time t. So it looks like we don't have an initial value. So the amount of water that is sprayed on the field, we're going to assume we're using a calculator here. If we were to integrate that rate function, then that's going to give me the net change in the amount of water on the field. Well, we started at time 0. We're going to go to some point in time t, and that would be the amount of water I have at any point in time. So if I need the amount of water at time 5, I'd integrate that rate function from 0 to 5, and that would give me the amount of water. Now, what you can also do is think about your units here. R of t was a rate that was in gallons per minute. dt is a time. So essentially what I'm doing here is I've got gallons per minute, and then I'm going to multiply by the number of minutes because that's what dt is. And when I multiply those two things together, I'm going to end up with a number of gallons. So that's one of the things that I like for you to use when you're doing these problem solving activities, is really think about the units in your operation, and it'll help you figure out whether or not you have things set up correctly. So B, it says how much water has been sprayed on the field during the first 10 minutes. Well, if we want to find the amount of water at time is 10, all we have to do is integrate from 0 to 10 this rate function. And again, I'm assuming we're using a calculator here. R of t has already been defined, so I don't need to rewrite the function. And when we plug that into the calculator, we're going to get about 227.971 gallons. Okay, so fairly simple to do. Okay, so there's one more problem here that I want you to try. And this one's actually a motion problem again. But remember, you can use a calculator on this, and that if you're allowed to use a calculator, you really should use a calculator because it's going to save you a lot of time. So we're given a position function here, and they are talking about rate of change, and they're also talking about average rate of change. So I want you to take a few minutes and try this out using a calculator. Okay, so here are the solutions for this one. So part A, it says find an equation that can be used to find the particle's rate of change at any time t. So essentially, I'm looking for the velocity function since we started with position. That one, you can't really use the calculator. You just take the derivative. Very, very simple power rule. We get negative 3t squared plus 14t minus 14. So B, it says at what rate is the particle moving when time is 4? Well, you could move it out, or you could work it out by hand if you want. But really, I would just actually plug in the position function into the calculator and then just have the calculator evaluate the derivative at time 4. You'd get negative 6. So remember, that means that we're moving to the left at a rate of 6 meters per second. Okay, part C, find the average rate of change. So again, average rate of change is just slope, essentially, change in position over change in time here. And we get negative 74 meters per second. And again, check your units there. Do they make sense? In the numerator here, I had positions, which are going to be meters. In the denominator down here, I had times. So I have meters per second, which is what I'm ending up with and which is what I wanted for an average velocity. And then part D, when's the particle not moving? Now this is definitely where the calculator is going to become useful. I just plotted my velocity function, and then I used the calculator to find those roots or the zeros, and that occurred at 2 times. About time is 1.451 seconds and about 3.215 seconds. Okay, so for your homework, as you work through these, I'm encouraging you to use your calculator. I want you to get really comfortable doing these things on the calculator. There are going to be some problems where maybe a calculator seems like it's going to be more work than it's worth because it's very, very easy to work out by hand. And if you want to do it that way, that's okay. But make sure you're doing some practice with the calculator so that these operations become things that are kind of seamless for you. The calculator is just a tool for us to take care of all the computation. We're doing all the calculus reasoning, and then the calculator is doing the computation that's giving us the result.